Thank you. Hello, can you all hear me? Excellent. Hi, my name is Sebastian. You already got an introduction. I'm from Sweden, which is why I've got a bit of an accent, but I've been here in Australia for nearly 10 years, and this year I'll actually be celebrating Christmas in Sweden for the first time in 10 years. I'm really not looking forward to the weather. As Luke was saying, I'm currently working at Culture Amp. It's been 3 weeks so far, and before that I was at Envato for well over 5 years, and for the last 2 or 3 years there I was heading up the software architecture efforts, and particularly around event sourcing. So today we're going to be talking about event sourcing with CQRS, which will include a little bit of DDD in it. I want to give you a more balanced view at both the upside and the downside, and we'll also be talking about this thing that you may or may not have heard of, which is called eventual consistency. So let's dive right in. What is event sourcing? Well, many systems that you're familiar with probably log events. You send it to a log file, or you store it in a database table somewhere, you send it into Splunk, you do something with it. But it's really important to know that event logging is not the same as event sourcing. Logging events, for whatever reasons, is not the same as sourcing events, because with event sourcing, we're forcing the current state at any point in time to be derived from the events that we have in our system. I want to mention this guy. His name's Greg Young. Most of what I'm telling you today is going to be his work. I offer very few original thoughts. It's mostly stolen directly from him. But he, even though he popularized event sourcing, he didn't invent it. Event sourcing as a concept is at least 500 years old. Greg says that he has tracked event sourcing back to ancient Mesopotamia, which is way longer than 500 years. I'm not sure about the Mesopotamia thing, but I do believe in the 500 years. And the reason for why this is true is that most mature industries, as we know them today, are already event sourced and have been for a long time. The finance world, the accounting world, insurance, medical, legal, all of these industries that are way more mature than our computer and technology industries are already event sourced. And the canonical example is, of course, your bank account. Do you think that the balance of your bank account is simply a column sitting somewhere in a relational current state database table somewhere? Really? It might be sitting there, but is that the source of truth for it? Because what if you disagree with your bank? What if you say, I actually think I should have $1,000, and your bank says, no, it's $100, the column says so. No. The account balance is an equation. It is the sum of all of the transactions that have occurred over the history of that account. And this is event sourcing. We can manually calculate, going through hand by hand, which is what they used to do when there weren't computers around, and add up all the debits and the credits, and we can derive the balance from that. And this is event sourcing. In event sourcing, all of your current state is transient. Your source of truth are the events, not the state. And in this context, when I say events, we describe things that have happened that are of significant interest to you. They are business facts. They're expressed in the past tense because they are facts. They are things that have happened. So in your bank domain, I know there's probably a few people that may already work at banks here, so you know your domain better than I do, but you'd probably see events that look something like this. New account application received, customer identity verified, we've opened an account, funds have been deposited, withdrawn, transferred, and we've issued an account statement, and so on and so forth. In another domain, the calendar domain, you probably all have calendars. We have appointments that have been scheduled and rescheduled, invitations that have been extended, sent, accepted, declined, etc., etc. At Culture Amp, what we do is we make it easy for people to receive and act on feedback from their employees. And so what we do is we send out surveys that measure employee engagement. These are some of the events that we see in our systems: adding new employees, launching survey, answering questions, and so on and so forth. With event sourcing, these type of events become the very center of your domain, and modeling them well is very crucial. Putting it more into practice, one of the other examples that I can give is if we were to build a shopping cart for an e-commerce website. That's what Envato was doing. We had a big e-commerce website. Well, they still do, but you know. The way that you would probably model this in your current state relational database, or in your document database, or whatever technology you would choose, is that you would have a cart model. It would have some line items that were associated with that. It would have a shipping address and so on and so forth. And we've been told, or at least I've been told, when I was learning how to do all of this, that the shape of this data is the most important thing. Being able to tease out these concepts and these things, that's the most important thing. But we can also express the same data in events. Here's our shopping cart. We start with an empty one, and then we add an item, and then we add another item, and then we provide a shipping address. And then we can build this from this. So using these events, we can rebuild this current state. But what we end up storing are the events. And all of this current state, all of this, that becomes disposable. It becomes a cache that can be deleted or regenerated at any time. And at the fundamental heart of it, event sourcing is nothing but a different way of storing information. But it is a different way that has fundamental consequences, because with event sourcing, all of your data is append only. And this is a big deal, because it means that all of your data is immutable. You can't change it. So what happens when there are mistakes? Because of course there are going to be mistakes. People do things that they shouldn't do, or they change their minds, or whatever. Well, my question back to you is, how does an accountant deal with a mistake? If they accidentally transfer $1,000 and they were meant to transfer $10,000, what do they do? Do they simply go back and add a zero to that initial transaction? No, of course not. That's not how the accounting world works. What they would do is they would then transfer an additional $9,000, or actually they probably wouldn't do that either, because that's not how accountants work. They would get the receiving party to transfer back the original $1,000, and then they would transfer the full $10,000 back again. And in event sourcing, we call these correction events. So in our shopping cart example, if we add an item to the shopping cart and we didn't mean to, or we changed our mind, we no longer want to buy it, we can remove that, and we do that by capturing this item removed from cart event instead. Now, are these the same thing? Anyone? Yes? No? No? The current state is the same, right? The actual result, if we run all of these events, is exactly the same. But they're different, right? In your system, the thing that you're going to go back on Monday and work on, can you think of two separate use cases that result in the same current state? If you can, then you're losing data. Somewhere along the way, you are losing data because you have two different use cases that end up in the same current state. Now, my follow-up question to that is, how do you determine what data you're happy to lose? And did you get your CEO's permission to lose that data? Chances are probably not. I try to never lose data. It's one of the fundamental tenets that I try to use in my career and with everything that I do. And I do this because I don't know how to value data. The data that we have today has potential future value that I can't qualify or quantify. And this is the main benefit that we get from event sourcing, is we don't lose it. Because at some point the CEO will come and say, you know what? People that have removed stuff from their shopping carts, chances are they might still want to buy that, right? So can we do like a direct marketing campaign to every user that's removed something from it, you know, all that sort of stuff. And if my world is current state, I would say absolutely, sure, we'll start capturing that data now and come back in 6 months and we can run the campaign. But in an event sourcing world, we can just go back, look at all those events, and we can write what we call a projection. And we'll talk more about what that is in a minute. The point is we're not losing data. And when we're not losing data, we can come up with very new and interesting ways to interpret that data over time. And we also get a time machine, which is cool. Do you want to know what the states of a particular thing look like? Approximately, I try to get the timing right, but it's supposed to be exactly 1 year ago, but I'm about 3 minutes out. Anyhow, no problem. We can get the current state of the system as of this particular point in time, because an event source system is deterministic. You're probably thinking, sure, that's all well and good, but it can't possibly scale. What if you have a lot of events? And that's where this whole CQRS thing comes in. CQRS is short for Command Query Responsibility Segregation. It's built on another pattern called CQS, which is Command Query Separation. Command Query Separation, or CQS, states that a method in a class is only allowed to ever return state or mutate state. It's not allowed to do both. CQRS is what I call CQRS is what I call CQS on steroids, which takes that same concept of separating the mutation and the returning of state to one level up or several layers up. Effectively, what it does is it separates reads from writes. And a famous quote that I really like to use when talking about CQS and CQRS is this: asking a question should not change the answer. Now, it's entirely possible to use event sourcing without CQRS. A lot of people get these two things conflated, and it's also really very possible to use CQRS without event sourcing. It's just that they go really well together. So bear that in mind as we talk about these things. They are not the same thing. They just go really well together. But in building out this architecture, there are 4 major building blocks that we're going to be talking about. Well, the first 3, really. The 4th we'll just mention briefly. So let's start with the event store. Events are kept in a database that's called the event store. I think that's pretty straightforward. The event store is usually considered a subsystem of its own right. There are both commercial and open source event stores available, but it's actually easy enough to roll your own. And that's what I've done for the most part. The simplest event store has a single event stream. So all of the events go into a single stream. And it has 3 single features. Only 3 features. You can put an event in it. You can get all of the events in order, starting at a particular offset, or you can get all of the events in order, scoped by a particular something, and we'll talk about what that something is a little bit later. These are all of the features of an event store that we're going to need. We're not going to need any others as we build out the architecture. So let's start with reading. Any system has clients that needs to read and display information. And clients are usually interested in current state. And I think it's not a stretch to try to convince you that the event store in and of itself which only has all of the events in order and so on and so forth, is not actually particularly suitable for presenting current state. So what we need is something that clients can query for current state. And we call this a query handler. And it's if we're drawing out our diagram, it's a little bit of a detour. Now, the way that this works is that the query handler kind of tails. It keeps listening to the event stream and keeps up with all of the events that are happening. And it uses this to build up a projection. And that could be your current state. And when a client wants to know something, the query handler just looks inside that projection. It doesn't look at the events, it looks at the prediction that it's built up, and of course returns that data to the client. And the query handler will build up multiple of these projections, and they tend to be optimized for a particular query. They're not a single, it's not a single one, there's multiple ones, and if you have multiple endpoints in our APIs or multiple screens or pages in our interface, we'll have a separate one for each one of those. And depending on what the query is, the query handler will pick the appropriate projection to return the data. And this little process that sits and tails, sits and listens for the events, they are individual and independent for each of these projections. It's worth noting that this is not using the observer pattern, if you're familiar with that. Instead, we're making use of this one feature in our event store, which is get all events in order from an offset. What happens is that these little things, which we call projectors, they keep a pointer or a bookmark to where in this big event stream they're at. So it knows how far along it is. The projections are disposable, and we can just throw away the data, reset it back to 0, and start it all over again. What this means is that these projectors and the projections are completely decoupled from each other, which in turn, there are multiple benefits of doing that, of course, but one of them is that it allows for different data storage options. Depending on what type of queries you have, you might choose a relational database or a document database or a graph database or a search engine or something like that. So all of these projections and the projectors can use different technologies. This means that we can optimize for how we want to read the data. And for many systems, this is very important. Because most of the current state read models that we see in monoliths and in big systems, they tend to be normalized, which is actually optimized for how we want to write data. We don't want to duplicate data, so we write it in a very normalized form. But projections can be, and often are, denormalized, which means that we are really optimizing for how we want to read the data. They're cheap. They're easy to rebuild. If we want to change something, we want to create a new interpretation of our data, it's fine. We'll just copy the projector and spin it up again, and we run them in parallel, and the new one builds up. And then we can eyeball the new projection and see, does it actually look like what we want? And if so, we just swap. See how easy it was? We just swap from one or the other. And then we just get rid of the old one. This means that we never have to do any database migrations on production tables ever again. We simply replace the tables with new projections when we need them. So, in summary, clients never query the events directly. Instead, they query denormalized projections that are optimized for querying. These projections are built up by projectors that process the event stream in order. They're completely decoupled from each other, and they don't share any state or often don't share code either. And they're cheap and easy to rebuild. So what about the other side? What about the command side and the writing? Because in addition to reading, clients often want to write data as well. And just as we established that clients should never query the event store directly, nor should they be writing into the event store directly either, because the event store is not responsible for validation, so giving clients direct access is kind of dangerous. Instead, what we have is clients expressing their intentions to do something in the form of a command. And just like we had something that was responsible for handling queries, we need something responsible for handling commands. And of course, you figured out the naming scheme. It's called a command handler. Now, commands express intent. And this is important because if we look at our events and how they are named, in the past tense, because there's something that's happened, the commands are named in the imperative. Instead of account open, we say open account. Instead of funds deposited, we say deposit funds. And this is the key right here. Commands represent intent and they can be rejected. Events are facts and they cannot. But when a command is accepted, they result in an event. Does that make sense? So how does the command handler validate commands? Well, this is where we start borrowing from DDD. Hands up, how many people have read the DDD book? I am so sorry. It's not a good read. I mean, I probably shouldn't say that, but it's not a good read. It's very dry, it's very boring, but it's so useful. Like the information that exists in this book is just amazing. So if you can stomach it, I would highly recommend trying it. There are some distilled versions as well, which are quite interesting too. Now, how we use DDD in our event sourcing world is that these events, they kind of have to happen to something. And that's something we call an aggregate. And this is a DDD term. This is what we're borrowing from DDD. And the aggregates are kind of the nouns in our system. So if we look at these events again, the account application received and customer identity verified, and we open an account and we deposit stuff and transfer funds and so on and so forth, then the aggregates that these things happen to is, of course, the account application aggregate, and the customer aggregate, and the account aggregate, and the transfer aggregate, and the account statement aggregate. In a calendar domain, our aggregates would probably be the calendar itself, but also the appointment, the invitation. At Culture Amp, our aggregates are, the employee, the demographic, the survey, the question, the response, comments and reports, and so on and so forth. And these aggregates, they have identity that need to be tracked over time. Often they have life cycles, which means that they have a beginning and an end. An appointment, of course, you schedule the appointment and then you actually have the appointment, and at that point, that's kind of like the life cycle of that aggregate. They often refer to each other, so there's meant to be an arrow in between there, which I tried to change last minute and clearly it didn't work. But basically the idea that a response is connected to a survey, or an invitation to an appointment is obviously connected to a particular appointment. So when the command is received by the command handler, it is executed against the aggregate. And the aggregate is the thing that determines whether this command is either accepted or rejected. And to do that, it needs to know its current state. So the way that works is we start by just loading all of the events for a particular aggregate, and then we instantiate a brand new instance of that aggregate. And we ask that aggregate to replay all of its events in order to constitute its own current state, and then we attempt to process the command against that aggregate. And that is either returns a true or a false. And if true, then we persist the event. Here are the features that we're using. We're putting an event into the event store, and we're getting all of the events in order, scoped by a particular something. And now we know what that something is. It's, of course, the aggregate ID. You're probably thinking, isn't all of this replaying slow? You're going to have to do it an awful lot. Yeah, it can be. But remember, first of all, it's only on writes, never on reads. And if we keep the number of events per aggregate low, we can actually mitigate a lot of these problems. I always think that an aggregate that accumulates an unbounded number of events over time is a smell that should be avoided. And wherever possible, we want fixed life aggregates so they can't just accumulate events over time. For example, we would not put the order placed event on the customer aggregate, because even though it's the customer that places the order, that would just keep accumulating events over time. So instead, for each order, we create a separate order aggregate that references the customer. Domain modeling is hard, and event sourcing doesn't change that. So often, a lot of the complexity in how to build event source systems is how do we create our aggregates and the events that are associated. So, in summary, clients never write events directly. Instead, they express an intent to do something via commands. These commands are validated by aggregates, which is a concept that we borrowed from DDD. These aggregates, they fetch events from the event store and replay them to reconstitute, rehydrate, we sometimes call it as well, their current state. If the aggregate accepts the command, it results in an event. So, where does this leave us? Well, this is what we call the circular architecture. Clients express their intent through commands. We just covered that, and they result in events. Projectors, they tail the event store, and they build up projections that the clients then query. This is what the architecture looks like. What this allows us to do is decoupling reads and writes almost completely. They can scale independently. We can take our whole query side, all of these projections, and we can replicate them in multiple regions, in multiple places, because they're read-only, right? Writes are fast, or usually fast, depending on how well you've modeled your aggregates, and they're always consistent. Reads are fast, and they're eventually consistent, and we'll talk more about that later. I want to cover very, very briefly the fourth building block in this architecture, which is called reactors. I don't have time to go into it in detail, unfortunately, but it's actually a really cool thing. We have to extend the architecture in order to talk about them. And they are kind of like projectors in that they tail the event stream. But instead of building up projections, what they do is they react to events. And they can react by triggering external behavior, like sending an email, for instance, or by emitting new events back into the event store. So for instance, you could have a reactor that sits and watches orders, and when it discovers the 10th order from a particular customer, it can issue another event that says, customer promoted to gold class. Or, of course, it can do both as well. Reactors are cool because they are single responsibility units that have very clear focus on implementing a particular business rule. And what they do is they encourage a business-oriented decomposition of the system. So, all in all, recapping, event sourcing makes you store business fact as the source of truth, and these facts are immutable. You can't change them once they've happened. Event sourcing makes the system deterministic. CQRS in the circular architecture is something that works quite well with event sourcing. Clients express their intent via commands, which, if accepted, become events and are appended to an event stream. Asynchronous projectors process the event stream and build up denormalized projections, which the clients then can query when they want to know something. And then we have these asynchronous reactors that process the event stream and reacts to events according to their business logic, often outputting new events. So, why would you want to do this? The first reason, I think, is because it treats the core of your business with respect. You can place no more respect to your data than placing it at the very core, at the very heart of your system, and then never change it. Walk away. We're not losing data that we can't value in the future because we can't predict the future. So the data that we're capturing today have potential value in the future and we're not throwing it away. The whole idea of event sourcing as well is compatible with reality. Not only have all of these industries been using it for hundreds of years, but event sourcing actually seeks to emulate the real world. Because just like in the real world, time is a first-class citizen. In the real world, the past is done, and if you don't like it, sorry. All you can do is compensate for it. You can't go back and change it unless you have a time machine, which, if you do, why are you sitting here listening to me? The real world is also eventually consistent because there is no central control. And the real world is made up by independent actors that do the best that they can with all the information that they have. I also think that this pattern allows for rapid iteration and reinterpretation because what we're effectively doing is we're separating the recording of what's happened from interpreting what that thing means. Interpretations and experiments are easy to get rid of when they're no longer relevant. Just throw away that projection. It encourages a bunch of good practices like separation of concerns, like through these isolated asynchronous components. It encourages code that is expressed in business and user terms. So all of these event names that we've been talking about are often how our business and product stakeholders think about the systems. They think in terms of events already. A customer goes and places an order, or they add something to the shopping cart. That's how they think about it. And what it does is it removes abstractions and forms a ubiquitous language between engineering teams and product teams, and business owners love this. It avoids a bunch of common pain points like database migration, ORMs, etc., and it allows you to use the best tool for the job, like whatever technology that is most suited for a particular task. You get a free time machine as well, which we've already talked about, which is kind of cool. Not the real kind of time machine, but in your system at least. But there are downsides as well. First of all, obviously, mistakes are forever. Makes sense. Natural evolution of event schemas will and do happen. And you can't change these events after the fact. So if you make a mistake, or even through natural evolution, you still have to maintain schemas and all of these things forever. If there are any mistakes, you have to create compensating events rather than doing the quick fix-up of just going into the database table and changing the column, which is both an advantage and a disadvantage in and of its own self because it discourages hacking, but sometimes you just need to fix the goddamn thing. There are strategies on how to manage this and deal with this, but they can be painful, and some of them are not for the faint of heart as well. Opacity is another big downside as well. Traditional relational models kind of mean that any developer or anyone really who's got some SQL knowledge and access to the database can just go in and poke around. You can answer questions pretty quickly, but an event store renders all of those tools and the ubiquitous access completely irrelevant, and this is actually a really big deal because the data that you have is way more opaque in your event store. And in order to make sense of anything, you have to create projections. We're going to go on a slight little, you know, what's the word? Yes, well, maybe. No. I'm going to go off on a tangent. That's the word I was looking for. We shouldn't conflate the inherent necessary domain complexity with accidental complexity. We can't avoid complexity. Our business domains are complex. If our business domains aren't complex, then we're in the wrong line of business because it means anyone can copy them. But we can choose how to implement this complexity. And we really need to avoid conflating the accidental complexity that comes from how we build systems with the inherent domain complexity. Now, one of my beliefs is that monoliths are kind of meant to be this simple arrangement of complex things. So why simple arrangement? I mean, it's usually one big thing that you go and you deploy and off you go, right? It's usually one or a couple of processes that you run, and it's kind of simple to deploy and get started with. But the things inside it becomes very complicated over time. Event sourcing with CQRS is meant to be kind of the opposite, which is that it's a very complex arrangement. There are a lot of these independent, autonomous actors, which each one of them is simple, but in aggregate, the arrangement of them is far more complex. Event sourcing with CQRS has a lot of moving parts. And you really have to beware of devolving into a complex arrangement of complex things. And this is the number one issue that I've seen. Your mileage might vary, of course. And it's really easy to get here because of the cognitive load that's introduced by this fundamental paradigm shift. So if you are a team who's used to building this simple arrangement of complex things, well, guess what? You're used to building complex things. So when you go and you try to build a complex arrangement of simple things, those things tend to become more and more complex. And many developers will struggle. And I've seen this in practice as well. And it doesn't help that it isn't mainstream. There aren't enough resources out there. There aren't enough conference talks or books or general information. I'm trying to fix some of that, but it's hard. I will say one thing though, which is that it's gaining traction. I've been talking about event sourcing for about 3 years now, and the difference that I've seen in that time, I don't think it was just because of me. I actually don't think it was because of me at all, but it's definitely changed over time. If you want to get started though, you're going to run into the J-curve of productivity. Has anyone seen the J-curve of productivity before? It's one of my favorite curves. It looks like this. Basically what it means is that things will get worse before they get better. And this is absolutely true. If you're embarking on a mission to build an event source system, you will slow down. Hopefully at some point, you'll get through that part of the curve where it gets better and you're actually saving time, but it'll take a while before you get there. And especially, how many people in the room are team leads or managers or architects or people that have the authority or power to impose things on other people? A few? Yeah, cool, awesome. Do not impose event sourcing on a team that doesn't have the buy-in, who doesn't have the stakeholder support, and who lacks the intestinal fortitude required to try something like this from the beginning. And then there is that other thing. That other thing that we're not supposed to talk about, but we do anyway. It's called eventual consistency, and I mentioned it this morning. Because commands are synchronous. You send a request, the command is validated. You issue a command, and you effectively receive immediately an ACK or a NACK for whether this thing happened or not. Queries are also synchronous, which means that you send a request, and it gives you a response from the projection. And receives that data synchronously as well. But the projectors are asynchronous, right? It can take some time before the command happens and the event gets stored in the event store for that change to show up in the projection. That's kind of shit. It just is, right? Now, the reactors that undertake all these complex business rules are also asynchronous, which is even more shit. And because all of these things are autonomous and independent and decoupled from each other, these changes can show up in different parts of your systems at different times, and that's triple shit. And when not all parts of one system has the same idea of what the current state is, This is what we call eventual consistency. The real world is eventually consistent. Just kind of by the by. Independent actors in the real world act without consulting each other. I'll give you an example. While you're talking to me, or while you're listening to me talk, your car might get stolen. In your copy of the world, right? Your car is exactly where you left it because you're not in lockstep with the real world. And hours from now, when you find that your car has been stolen, that's when your copy of the world is made consistent, and this is eventual consistency. The interesting thing, though, is your system, whether you already know it or not, or whether is that it's already eventually consistent. Once you let go of a database connection and you're figuring out how to return that data back to the client, that data could already change on you. So the data that you're actually sending back to your client could be out of date and you don't know it. The data that sits on the web page could be out of date and the client doesn't know it either. We can narrow the time window for all of these eventual consistency, but we can't eliminate it completely. And if we can't eliminate eventual consistency, all we can do is manage it. And modeling systems here, based on the real world, is very helpful for dealing with eventual consistency because the risk with eventual consistency is a function of time. When people complain about eventual consistency, I say, is 1 nanosecond of eventual consistency okay? What would you say if I asked you that question? 1 nanosecond of eventual consistency, is that fine? Is that okay? Yeah, people usually say yes, cool. What about 1 month? Is that okay? No. Cool, awesome. So that means that somewhere in between 1 nanosecond and 1 month, we have your threshold of what an acceptable level of eventual consistency is. And this threshold is contextual. Of course, it depends. If we're showing an order status to a user, we probably want that to show up in a matter of seconds, right? At the very most. Because if we don't, they might accidentally think that it hasn't gone through, and so they try to buy it again or something like that. But if we're showing a sales report to a marketing team who's trying to figure out what marketing strategies to do next, then probably an eventual consistency of a couple of hours is not a big deal. And all of this is a business risk, not a technical one. And the key question to ask is, what is the risk of making a decision with out-of-date information? Now, there are ways to manage eventual consistency as well, and there are 5 main ones. The first one is educate your users. Every email newsletters you've ever subscribed to do a really good job of educating you on eventual consistency. Because when you try to unsubscribe, it says, please allow for 7 days for this to take effect. That's eventual consistency. You can lie to your users as well. You know, depending on your use case, that's probably valid, or might be valid. I call this read your own rights. So the client knows that it just made a change, and the client knows that that change was accepted. So you can cache that bit of state in the client, in the browser or somewhere, so that they see what they think is consistent while the rest of your system catches up. You can build new interfaces that de-emphasizes the whole idea of immediately seeing a response after you do something. You can slow down the user. You can show spinners for them if you want. That's also a valid strategy. Or you can, of course, speed up the backend. But while all of this is manageable, while there are strategies, while the world is eventually consistent, it can be an absolute blocker and an absolute issue for people, and it could mean that you can't build this sort of architecture. At the end of the day, event sourcing in CQRS is a pattern. I want to emphasize that I don't think it's appropriate for every single use case, and it's absolutely not a silver bullet. I think that it's got a lot of awesome benefits, but also significant disadvantages that have to be taken into account. But if you can overcome these challenges, it's incredibly powerful. One of my former colleagues now at Envato said this, which I think is really apt. He said, event sourcing is a multiplier. If you do it well, it gives you magical powers in terms of flexibility and scalability. But if you do it poorly, it becomes worse than the crappiest ball of mud. This is the sun. Well, there's an emoji of the sun. But it's a warm day today, right? The light that you see today, the heat that you feel when you step outside, was light that left the sun 8 minutes ago. The sun could have exploded 6 minutes ago, and we don't know it yet. Right? We'll find out very soon. This is eventual consistency. If you look for eventual consistency, you'll find it everywhere. When you walk out this door, you'll tap on an iPad. Hopefully you select green, but that you know at that point in time what you're voting. I will know at some point what you voted, not you specifically, of course, but in aggregate. And that's also eventually consistency. I will eventually be brought up. I will be eventually consistent to the feedback on my talk. And that's really all I have to say. Thank you very much for listening.